Yes, yes. Alrighty, good morning. We're going to go ahead and get our review session underway. Oops. Alright, let's take a look at all of these questions. Alrighty, so it's basically Sarah and Becca who are getting all of the questions here, which is alright. They're going to do well. And the creature is at it again. Alrighty, so... One second. Go, leave him alone. Go, get out of here. He's still eating his breakfast, that's why. Okay, so looks like we have propane burning. We have 35 grams being produced from 25 grams with excess oxygen. What's the yield? So first things first, we need to balance it. So we have our... Oh my gosh, it's so funny listening to Oz like grumble like that. Oops, 8 here and 2 here. We have 2 and 3. Alright, so if we make this 3, that becomes like that. If we want that to be 8, we're going to have 6 plus 4 is 10. So we'll need 10 oxygens by making this into a 5. Oz, relax, dude. So, now that we have our coefficients, we see that there's a 1 to 3 relationship between propane and carbon dioxide. So, we are going to need to figure out our theoretical yield, because it looks like the 38 grams that's there is our actual yield, and 22.05 grams is what we're starting with. So we're going to need to find our theoretical yield first. So 22.05 grams of propane. Need the molar mass of propane. Just 3. Oh my gosh. We'll say it's 44. So you see it's half a mole-ish. Creature, stop it. This is like our very last stream too, and they couldn't just shut up for, 2 seconds. Interestingly enough, the molar mass of carbon dioxide is also 44. So that's going to make the math super easy. So this means 66-ish grams, because everything else is the same. So with this, the percent yield we're going to get. So we're going to say that that's our theoretical yield. So percent yield is actual over theoretical. And so if you do this math... This guy's vocal range, he should be in like a song troupe or something. You're a music major. Doing this, you get 57.6%, we'll say. If we're looking at the answer choices, yes, we have 57.6 as an answer choice. And so there we have it. So I guess points there was figuring out what the numbers meant. So 38 there was an actual yield since it was produced. And then, of course, the 22.05 you're starting with. And then I suppose balancing the equation there. All right, so not the easiest problem to start us off with. All right, what is the reducing agent in this following reaction? Okay. So I'm just going to copy it without balancing because we don't need that. Dichromate, 3 nickel, So 3 nickel, 2 plus 2 Cr3 plus 7 water. Okay. So, if we're going to, I'm sorry, that's a Cr. If we're looking at this, we only have 3 options, right? So, only reactants can be agents of something. So, already we can get rid of any of the products as options. The reducing agent is the one that is oxidized. So let's go ahead and see if we can't get any oxidation numbers out right away. For the Cr207, we can figure out what those are going to be. The chromium we don't know. It's a transition metal. So 2Cr plus 7 times -2. So minus 14. Oops. Plus 12, Cr is 6. We can see already that Cr is becoming 3 on the other side, but that's reduction, right? That's not what we're looking for. If we look at nickel, though, it's going from 0 to plus 2. That we can just see right away as well, hopefully. And so that's our oxidation, which means that nickel is the reducing agent. So remember, whatever is oxidized is going to be part of your reducing agent. So you want to go to your reaction, see in your reactant side which of those has the element that's being oxidized. In this case, it's nickel by itself. If we're asked for what's the oxidizing agent, we would say dichromate, because it contains the chromium that is being reduced. Okay. Next one, which is a redox reaction. Alrighty, so let's take a look at these, see what we can do here. So 14 has 3 options. A is some double displacement. I'm not even going to write it. We have two PBR. Actually, we don't need the... Oh, that's weird that it didn't include the 2 there, but it doesn't matter. And then we have the copper plus sulfur. All right. So, double displacements, remember, are always non-redox. Hopefully we can look at it and see that it's double displacement because we have 2 ionic compounds reacting together, and we're even given the products here. We can see that it's 2 more ionic compounds that are produced. So double displacements are never redox, so we don't even have to look at that. The next one we want to look at is are the other 2. We want to look at their oxidation numbers and see if they're changing or not. Here we have an oxidation number of +1 on lead, -1 on bromine. Good morning. And if we look on the other side, ionic compound here, we're ending up with +1 and -1 on those 2. So that's also non-redox. And just by elimination, we'll have ruled C as the redox reaction here, just because none of the above is not an option. But let's just make sure. These are elements by themselves, so they start as 0. They end up as +2 and -2, so that is definitely a redox reaction. And so we're going to end up with just C as our option there. All right, if any more questions come up as we do these, as I go over them, I'd be happy to address those. Okay, so we have... next is, okay, so we have 31.5 mils of sulfuric acid, unknown molarity. We have a base of 0.0134 molar, And it took 23.9 ml. Okay. And then blah, blah, blah. So we want to figure out the concentration of that acid. First things first, let's write a reaction. Hopefully with all the practice you guys have been doing, reaction writing should be pretty quick. Remember, these acid-base ones produce just water and then some other ionic compound. They're just double displacement reactions. So this is we only need to know the coefficients for NaOH and H2SO4 here. So with that, we can go ahead and start working on this. If we want to do a plan, we know information about NaOH. We're looking for information about sulfuric acid. And we're given the molarity, which means we need to use the liters there to figure this out. This is our reaction coefficients. This is our molarity. Remember, when we're solving for molarity, we want to just solve for moles first, and then we'll divide it by our liters to find the molarity that's asking for. So let's do it. We have 0.0134 moles per liter. It's given to us in the problem. This is NaOH, so we have 2 moles of NaOH on the bottom. 1 mole of sulfuric acid on the top. Bust out your calculator. 0.0239 times 0.0134 divided by 2. Get some real small number. And now we want to divide that number by our liters. It looks like we had 31.5 milliliters, so 0.0315 liters gives us 0.0315 as our answer there. Alrighty. And so let's see, did we 15. Hold on, did I divide something wrong here? That's not an option. Alright, let me plug it in the calculator again. 0.0239 times 0.0134 divided by 2. That number divided by the liters of sulfuric acid, 0.0315. Ah, okay, so something went wrong with this. So I get 0.00508, yeah. 0.00508. I think I must have forgotten a 0 or something, so. When your answer choice is not there, double check your calculations because I had typed it in wrong. Go figure. Now I have the right answer. Okay, let's go on. Alrighty. So, stoichiometry, our favorite topic. Alrighty, solid aluminum gaseous oxygen produce this. Okay. For aluminum plus 3 oxygens, 2Al2O3, aluminum oxides. So we have 2.5 grams of aluminum, 2.5 grams of oxygen. We have information about both reactants. That tells us this is a limiting reactant problem. So we've got to do it for both. So our first one, we're going to want to go from our aluminum. And it's looking for the mass at the end of the problem. So that's kind of what our plan is going to look like. And for the other one, it's going to be the same thing, except we're switching out oxygen instead for the first part, instead of aluminum. So here we go. 2.5 grams times aluminum, where are you? 26.98. One mole aluminum. We have 4 moles of aluminum on the bottom, 2 moles of aluminum oxide, molar mass of aluminum oxide, 2 times 26.98 plus 3 times 16 is 101.96 grams, 1 mole on the bottom. Here we go, calculator time, 2.5 divided by 26.98 divided by 2 times 101.96. And you get 4.72, thereabouts. We'll just leave that one alone. Do the same thing with oxygen. That's going to be 32. For oxygen, it's 3 on the bottom. And then we already have our molar mass from before. Okay, here we go. 2.5 divided by 32 times 2/3 times 101.96 is 5.31. So therefore our answer is 4.72. I lost the question. All right, and so hopefully that was one of the options. I would hope. So that's going to be our answer there. All right. Is that the last one there? Yes. Okay. All right. So we always want to choose the smallest one, right? Next question. What's the coefficient of nitric acid in this? All right. So we have HNO3 plus calcium carbonate. So notice this is a hold on, let me just write all this stuff out first. CO2. Remember when you see these guys, that's the same thing as saying carbonic acid. Remember, but carbonic acid decomposes. It's going to be a lot easier to balance if you keep it as carbonic acid. So let's go ahead and just do that. That's going to make our balancing a little bit easier. So we've got hydrogen, we've got nitrate, we've got calcium, we've got carbonate. So let's see what we've got. We've got 1 on the left, 2 on the right, 1 nitrate, 2 nitrates, 1 calcium, 1 calcium, 1 carbonate, 1 carbonate. As again, leaving it as carbonate or carbonic acid, it's going to make it a lot easier because otherwise you're looking at CO2 and oxygen, or CO2 and water, and so it's just going to make things a lot more difficult for you because then you can't use the polyatomic ions anymore. So let's balance. Need this to be a 2, which will make that a 2. Looks like calcium's okay. Looks like everything else is okay, so our answer there is 2. So remember, if you see this as a product, that comes from H2CO3. If you balance it as H2CO3, it's a lot easier. That'll go the same thing if you have H2SO3 or NH4OH. Those would also be ones that form gases, but we want to, when you're balancing it, keep it together first. It's just going to make things a lot easier for you. Okay? Let's see. Okay, we've got calcium carbide and acetylene. Okay. Okay, so the reactions there, we have 13 grams of acetylene, and we're just looking at how much water that's going to take for mass-wise. So we know we have grams of acetylene. We're going to need to make that into moles, always to moles, right? That's the whole point of this chapter, or of that chapter rather. We're looking for moles of what we're looking for, and then it's asking us for grams, so we want grams of water at the end. So that is our kind of plan. So we have 13 grams to start. Molar mass is about 16. 12 plus 12 plus 2, 1 plus 1. It's about 26. Half a mole. What are we doing here? Okay, there's our... It looks like we have a 2-to-1 relationship here, according to our reaction. And then molar mass of water, 18.02 grams. Since it's multiple choice, you can leave it as 18. You don't have to worry about all these pesky decimals. So in fact, it's going to be 9. No. It's going to be just 18. Just looking at that. Don't even have to do the math. 13 over 26 is 1/2 times 2 is 1. 1 times 18 is 18. So apparently we're going to look for about 18 grams there. Okay. So, yes. It's always the stoichiometry, right? Okay, I just did that one. Let's get this one. Okay, similar problem, but now we're looking at gas stuff instead. So we have calcium hydride reacting with water to form hydrogen gas. We have the equation there. How many grams of calcium hydride are needed to generate 48.0 liters of hydrogen gas? So 48 liters of hydrogen gas at these temperature and pressures. So we can go from liters to moles. This time though, it's not liters of solution. This is PV equals nRT. You don't have a molarity. So definitely can't do that. And then we have molar mass on this side. So 40. So remember that N is going to be PV over RT then. So if we want moles of hydrogen, that'll be the pressure. So 0.995 atmospheres. The volume is 48 liters. R. And then the temperature is in Celsius. So that'll be 305. Yes. So remember, we need to make that into Kelvin. All right. So that's going to be our moles of hydrogen that we're going to be left with. So we need to cancel that out. In this reaction, we have 2 moles of hydrogen for every 1 mole of calcium hydride. And then we're looking for the mass. So let's see, calcium, where are you? Oz, shut up. Calcium is about 40, so we'll just say 42. Thereabouts. Remember, with multiple choice, you are given the option to not have to actually say 40.07 plus 1.008 plus 1.008. 42 is fine. It's multiple choice. Nothing's going to be that close of an answer that having 42 as your molar mass is going to be a problem. So save some time there as well if you can. Okay, so here we go. 0.995 times 48. So I typed in 18 divided by 0.08206 divided by 305 divided by 2 times 42. Do this, you get 40.07, and hopefully that's an answer. Yeah, it looks 40.1 is what they want, so round that to the appropriate sig figs. And there's your answer. So another thing also, make sure that when you're inputting everything in your calculator, it's a lot of multiplication and division. So make sure you understand how your calculator works. Because if you type something wrong, you might accidentally end up multiplying by 305 instead, and that's going to throw your answer off. So it's very important. I mean, it's kind of last minute, but always, always, always practice all of these on your calculator. So you understand how your calculator works, because that's what's going to be there for you on your exam. So just make sure that you are getting these answers as they're written out with your calculator. So, and I know that a couple of us have figured that out with some parentheses problems or whatever with the logs. So I'm glad we've done that. Alrighty, next one. At STP, 11 grams of sulfur. Oh, we're on gas laws now. Okay, sulfur dioxide of a volume of what? So remember, at STP, any mole, 1 mole of gas will have 22.4 liters. So if we want to go ahead and do this, we're going to need that grams into moles. Sulfur's 32, oxygen's 16, so that's 64. So the trick here is remember that conversion factor, the 22.4. So 11 divided by 64 times 22.4, we get 3.85. Is that an answer option? It is. So that's what we're looking for there. So remember that for gases, any gas will occupy 22.4 liters if it has the quantity of 1 mole. Remember STP standard temperature and pressure, 1 atmosphere, 0 Celsius. Alrighty, so in the diagram below, helium atoms are represented by unshaded spheres, neon by gray, argon by black. Total pressure is 900 millimeters of mercury. What is the partial pressure of helium? So looking at this, we have 10 total dots in there. So each dot would represent, we have 900 millimeters of mercury divided by 10 dots, just because it's a picture. So each dot is 90. If we want to see what's helium, we're looking at the unshaded ones. My eyes are kind of terrible, but I think I see 2 of them. And so that should be 180 or so. If you really wanted, you could see that it's 20% helium, 30% neon, and 50% argon. You could have done it that way by understanding that it's going to be 0.2 times your total pressure. But let's make it 3rd grade math instead, because why not? I know, so that may not be so obvious, but that's okay. So, or we could say, you can see that the X for helium is 0.2, just by looking at all of those. We see it's 2 out of 10, so 0.2. And the partial pressure would be the mole fraction of helium times the total pressure. So 0.2 times 900, and you get the same answer. Okay? Or you can do it by counting the dots. So that'll work too. All right. Next. Gas at 5 atmosphere, 5 degrees Celsius, and then it's now 40 degrees Celsius. Okay. This is a combined gas law problem. How do we know that? Because something is changing. So we have something is changing. That's how we know to use this one. Whenever you have something changing, in this case our temperature is changing, this is the law we want to use. So we have pressure and temperature. So because the volume is the same, you can get rid of it. If we want, you can just eliminate it from our equation. So don't need to worry about that anymore. Make the method a little bit easier for us. All right, so the only thing that we have left to do is we have to convert those to Kelvin, right? We can't use Celsius for gas laws. So we have 278 for one of them, and then 40 with the other one, which is going to be 313 Kelvin. So originally our pressure was 5 at 278. That looks like a J. Solving for P2. 5 times 313 divided by 278. We have 5.62. They're about 6.3 maybe. And what is our potential answer? 5.63. Yeah. Okay, yeah, because it was 5.29. So we'll round it to 3. Good enough. Remember, multiple choice, rounding is fine. So we would also, we can eliminate 2 of the choices there because it's heating up. Remember that if you heat up something, it's going to increase the pressure. So you can always eliminate the lower pressure options there because you know that the pressure is going to go up when you heat it. So always a good idea to kind of, think about it first, and eliminate some answer choices. So even if you have to guess, you can at least have a higher chance. So, alrighty, let's look at the next one. How many grams are held at this thing? Okay. So it looks like we're at STP. We can cheat here. So we have 150 liters. We're at STP, so we can cheat. Always cheat if you can. Don't listen to me. We're asked for grams of chlorine gas, so we need to convert from moles of chlorine. 35.45 times 2 is 70.90. Remember, if you're at STP, you don't need to do the ideal gas law. Save your time and use the shortcut. 22.4 liters is your shortcut for STP. So if you've identified this problem at STP, then you don't have to worry. Otherwise, you'll have to plug in the gas law, do all the calculations. It takes more time. So use the shortcut. All right, let's do this. 150 divided by 22.4 times 70.9. That equals 474.7. Yeah, 474 is an answer choice, so there we have it. Ta-da! So you can see, hopefully, setting it up this way is a lot faster than setting up with the ideal gas law, which you could do. You're not going to get it wrong, but it's just going to take more time that might be better served answering other questions. So always in timed exams, right? That's always how it works. Okay, next. Something has a pressure, volume, temperature. Okay, what's the molar mass? Okay. So just so we remember, molar mass is grams per mole. We have 1 gram already in our problem, but we don't know the moles. So we're going to have to wait on that first. So let's find our moles. We have pressure, volume, and temperature. 2 of those are in the wrong units. 35.8 millimeters of mercury. Can't use that. We need to make that happy. And then the temperature is 298 Kelvin. Okay, let's go ahead and find this pressure. 35.8 divided by 760. 0.0471. Okay, now we can do this stuff. So, moles PV over RT. So 0.0471. Our volume was 20 liters. R. And then the temperature. Let's do it. Times 20 divided by 0.08206 divided by 298. We get 0.0385 moles. So since our molar mass is always grams per mole, right? That's the units of molar mass. We have 1 gram, so we just need to do 1 over our answer. $25.96 and 26. That's fine. And so there we have it. So again, remembering molar mass, you have your units here: grams per mole, grams over moles. We have grams. We need to find moles using the ideal gas law. Once we find that, we can plug that in to this equation, and then we'll end up with our molar mass. Alrighty. What is the pressure of this thing at these things? Okay. So we have 1 liter flask, so we have volume, 0.60 grams of helium, so we can get moles, and 25 Celsius, we can get temperature. So we can figure out what this is going to be. So we have 0.60 grams. We need to convert that to moles. If I remember correctly, that's 4 grams. So there's our moles. We have 1 liter, and then we have 25 degrees Celsius. So all of these, again, it's just getting things in the right units so that you can use your gas laws here. So N 0.15, R 8206, temperature 298, volume is 1. Alright, so 0.15 times 0.08206 times 298 divided by 1 gives you 3.668. It looks like this one does have units of atmospheres, and 3.7 is the answer, so 3.668. Yep. Just round that to 3.7, and there we have it. Alrighty. This was, which one did I just do? That one was 18, I think. Okay, for her. Okay, next one. What is the change of boiling point of this into that? And we have density and KB. Okay. So we're looking for delta T. Is this boiling point? Yes. Well, we also know we have Kb times molality times the Van 't Hoff factor. We have glucose, so I is 1. Kb is 0.512. We already have that. So we need to find the molality of our solution. Remember, molality is moles of solute per kilogram of solvent. So it's told us that the density of water is 1, so 150 milliliters is 150 grams. So that's 0.15 kilograms. And so we need to find our moles here. So we have 14.7 grams of glucose. If you do its molar mass, you get 180. I can zip through this. Again, it's expected that you're going to take 30 seconds to figure out its molar mass. But in the interest of time, I zip through it. So we have our moles here, whatever those happen to be. 0.08157. We have 150 mLs of water. For water, density is 1, so they're the same, mils and grams. If we want to go to kilograms, that's just divide by 1,000, right? So our molality is going to be 0.00817, 0.08157 over 0.15 is 0.5438. So if we go ahead and plug that into our formula, I was 1, and then we just need to multiply by kb, so 0.512. We do this. 0.278. Let's see if that's an option there. 0.279, so yes, good enough. So we take this number, throw it back into our formula with the rest, and we can just plug and chug. Alrighty, next. How many mils of this molarity provide that many moles? Okay. Remember, molarity, it will convert between moles and liters. We're given moles, so we need to find liters, so we're going to put our molarity upside down. So 0.665 moles. We have 1.15 moles for every 1 liter. That's what molarity means. In this case, it's upside down because we're looking for liters. Moles cancel out, we're left with liters. And so doing this 0.665. Oh, this is actually also asking for milliliters, so we need to solve for that, or you can do that part in your head, but 0.665 divided by 1.15 times 1,000 equals 578.2. And 578 is one of our answer choices, so that's the one we're going to go with. Okay, almost done with this selection section. Calculate the molality of this thing in that thing. Okay. So molality, remember, moles solute, kilogram solvent. So we have 19.9 grams of KCl. I feel like half of this exam is just calculating molar mass. Alright, potassium is about 40. 39, we'll say. 39 and 35. Okay. 39 plus 35 is 74. Wow, and I wrote 3. Thereabouts. Again, save some time. Don't worry about the decimals too much. In fact, it's going to be maybe about 0.5 because the chlorine is there, whatever. It's not going to make a huge difference. 19.9 divided by 74.5, 0.267 moles. We have 750 mLs of water, which is 750 grams, which is 0.75 kilograms. So if we divide these two together, You get 0.356. Hopefully is an answer. Yes, there it is. And so that is the answer we get. Next. Comparing that much. Okay. Okay, so in comparing this is a conceptual question, so I don't really have all of the answer choices, so but we can compare. So we have with conceptual questions, it's useful to see like why some of them are wrong, and that can help you choose the right one. And then we have 0.25. So the only difference here is that we have different I values, right, for Van Hoff. So remember, the more particles you have in solution, that's going to increase your boiling point and decrease your freezing point. So comparatively, this one will have a higher the calcium chloride will have a higher boiling point than the sodium chloride, and it will have a lower freezing point. Remember, it expands it in both directions. So conversely, if we're comparing these, the sodium chloride will have a higher freezing point and a lower boiling point than the other one. So whatever mix of these is the right answer, that's the one that you want to go with. So I don't know what the answers are, so or the other options. So, but I can tell you that it says calcium chloride is a higher boiling point and sodium chloride is a lower freezing point. That's not true. Those are both for calcium chloride. Both solutions have the same boiling point. No, definitely not true. And so with the other two are, I'm not sure, but you'd have to work through it same way. All right. Looks like, Becca, we did the aluminum and oxygen one, so I'm skipping that. We also did the calcium hydride one, so I'm skipping that. And we have the glucose in water, so I'm skipping that. Aha, I have a new one. Okay. This is your question one for who knows what exam. So we have all these specific heats. Okay. If the same amount of heat is added to these things, what one will reach the highest temperature? Okay. So let's look at our... let's see how these are related. So if we want to kind of separate these two, if we do this, is that right? Did I divide both sides by, yeah. Nope, Q over MC. That's the problem. So if we want to look at what's going to have the highest final temperature, assuming that the temperature initial is all the same for all of these guys, which it is, we want to look at what's going to have the highest temperature. And so, as a result, if we see here, it's in the denominator of our equation. And so, we see here that if C is large, then Q over MC is small, right? And so if we add a small number to our initial temperature, that's a small increase in temperature. But if C is low, then we see that this factor gets a little bit bigger, so that's going to give us the biggest value. So we're looking for the smallest heat capacity gives the highest temperature here. So if we look at these options, the smallest heat capacity we have there is gold at 0.128, and so that'll be our answer. So in this case, it's gold. Okay. So that's the point of all these formulas, is that you can understand relationships between these variables. Solution has density of 0.1, excuse me, 1.22 grams per mil. What volume has that mass? All right, so density is your conversion factor between mass and volume. So we have a mass, we have a density, (48.2 divided by 1.22). 39.5. Yes, that's the answer we're looking for. Here's your density right here. If you wanted, you could use the formula, but it's just easier to use it as a conversion factor because you just got to set it up so grams cancel out and mils are left over, and that's what we do. Jet fuel has the same type of question here. We have another density one. You hate density, it seems. That's okay. So we have a mass of that many things. What's the volume? Okay, so 97.5 kilograms. Need to convert that to grams. Once we have grams, we can use it. We have a density of 0.804. Again, always arranging these such that everything cancels out. 97.5 times 1,000 divided by 0.804. We get 121,268. 121,268. And so we're looking for 1.21 times 10 to the 6th. Yeah, that'll work. Or should be should be 10 to the 5th, right? Is that? Oh, it is 10 to the 5th. Okay, I can't see the answers. So I see the problem is there that you just put kilograms instead of grams. So that's the only thing. So don't forget this guy. So, yeah. I told you all this metric stuff would be important. No one listens to me. But as you can see here, I mean, again, it's the end of the class, but we can see that the majority of all this that we're doing is all unit conversion. That's the entire class is just how to convert between units. And then there's occasionally some formula, what's the molality of this or whatever, but by and large, it's all unit conversion. So if you were going to continue on into 111, you really want to make sure you get this unit conversion down because it does not stop. It gets more and more and more unit conversion, unit conversion, unit conversion. So that's all we have. Alrighty, so we made it. I was not sure that we would make it through all those questions, but we zoomed through. That's the benefit of this. If you have videos, you can slow it down or pause it and then work through it yourself and then go on to the next one. So we have some benefits there. But yeah, we're good. So I don't see any more questions. So this is our last stream. So sad times. Your exam, remember, take it Monday or Tuesday. Or if you really want, take it Monday and Tuesday by starting at 11 p.m. on Monday. Maybe not the best suggestion, but you could take it any of those. It's open for 48 hours, so find your time slot that you want to do it. I think it's, 2.5 hours that I've given you, so you should have plenty of time on this. Feel bad for the 113 students who have 60 questions in 95 minutes. So they have an hour and a half to do more questions that are more complicated. So pity them. So alrighty, well, that's it then. So best of luck on your studying. Best of luck on this final and your other finals. We've done it. We've survived another semester of COVID chemistry. So, woohoo. Next semester we're still online. Maybe the semester after, maybe we don't have to be. We'll see. Hopefully. But I think you're probably going to need to get vaccinated if you want to come to class in the spring if it's offered in person. So plan for that, I suppose. So, alrighty. If there's nothing else, then it's been fun. Good luck on your on everything, and yeah, we'll see you. I guess I won't see you, but good luck on your exam.